Good evening, and welcome to the Scientific Adventures of Beardman. Well, today we're going to be looking at Newton's third law. And Newton's third law really defines what a force is, to some extent. Now, there are four basic forces, right? There's the strong nuclear force, the weak nuclear force, the electromagnetic force, and the gravitational force. At least you'll still see all four of those listed in a lot of textbooks and various things. Of course, we've learned that the weak nuclear force and the electromagnetic force are really the same thing, and we're starting to understand all of it better, although there's still a little ways to go. But anyways, all of those forces we can understand to some degree using magnets. Magnets, most of you have played with at some point in time because you've got a bunch of them stuck to your fridge, and it's a mystery as you're growing up, and you're like, what is this thing? You put it here and it sticks to the fridge. And, well, that's pretty cool. So you take them and you start playing with them, and you find that you can bring them close, and all of a sudden, thump, they attract. Well, like you can see up there. By the way, these are two animal butt magnets from our refrigerator. My father-in-law thought it was a very clever and funny idea to give to my 2-year-old son. And so, there, that's what's on our fridge, animal butt magnets. I guess it is kind of funny. Anyways, so you can see how as they get close, all of a sudden that force gets strong enough that it can overcome the force of friction on the granite countertop that they're sitting on, and they both move together. You've never taken two magnets and brought them towards each other, and one of them moved, one of them was pulled. They're both pulled together. Or if you flip one of them around, they're both pushed apart. Both of them. Forces seem to come in pairs. Okay, well, perhaps it's more accurate to say that a force is really an interaction of two objects. Like the two magnets. The two magnets are interacting. As they do that, you could say that each of them is experiencing a force. That's how we tend to say it in physics. The force is half of that interaction. Okay? Now, so as the magnets are being pulled together, most of the time, if you've got two equal-sized magnets, it's easy to see that they're pulled the same amount. Well, it turns out that in every single interaction, whether that's a gravitational, electromagnetic, weak nuclear, strong nuclear, every interaction, both objects experience the same force in opposite directions. Like we saw here, the animal butt magnets are both attracted to each other. Or like you've felt many times as you tried to force two magnets together that didn't want to go, both of them are pushed away with approximately the same force. Well, with exactly the same force. You can tell it's approximately the same force by feeling it. I'm now telling you it is actually the exact same amount of force. And this is what Newton's law is that in this interaction between two objects, there's an equal and opposite force on each of the objects. Now, well, I guess we should phrase Newton's third law the way you hear it a lot, and that is, for every force, there is an equal and opposite force. Or when object A pushes on object B with a force, object B pushes on object A with an equal and opposite force. Okay? So the two magnets get pulled together, equal forces, opposite directions, or they're repelled, equal forces, opposite directions. So now, why don't we notice this? When I push on something, like I push on the wall, or little z pushes on me. Yes, this is a Bengal tiger. But somehow my wife and I didn't realize that when we bought it for our son when he was 0 years old. Or maybe we got it given to us. I can't remember. I'm sorry if you're the one that gave it to us. We've forgotten. But we thought it was a zebra. Yeah. White, black, white stripes. You get it. Anyways, somebody pointed out, no, that's a Bengal tiger. And we realized they were right. So henceforth, this is little Z, the Bengal tiger. Anyways, little Z pushes on me. Okay? When he pushes on me, what exactly is going on? Okay? Or I push on a wall, or a car hits a light pole, or whatever it might be. Okay? Anytime there's a force between two objects, what's going on? Well, when little Z puts his little paw up to my cheek, and he pushes on my cheek, let's zoom in and look at what's going on. Okay, so here we can see little Z's atoms in his little paw getting closer and closer to the atoms in my cheek. And when they get close enough, just like the magnets, they repel. Because the nuclei of little Z's paw and the nuclei of the atoms in my cheek are both positively charged, and so they repel. So when we see something pushing something else, if we can imagine the molecules and atoms getting close to one another, those, let's just say each fingertip is a nucleus, as those nuclei get close, they'll never actually touch. They're like those two magnets. Hopefully that makes it a little bit easier for you to realize that if that's what's going on, well then the force from one must equal the force from the other. Okay, because we could see that and understand that better with magnets. Now we can see that a little bit better and understand that a little bit better with two objects like little Z's paw and my cheek. And this is true for any two objects. There's if you put a force, object A, little Z's paw, puts a force on object B, my cheek, well, my cheek puts an equal and opposite force on little Z's paw. Okay? So my cheek is pushing his paw that way, his paw is pushing my cheek that way. And that is Newton's third law. Okay? So no matter what the situation, no matter how much you've been convinced that one thing is pushing on the other and not the other way around, begin to try and see how, when one object pushes on a second object, the second object pushes back on the first object with an equal and opposite force. Good luck applying that in the things you see this week. We'll see you next time on the Scientific Adventures of Beardman.